Let's take a look at problem number 3. Some theory questions here. The first one is looking at h is equal to f of g of x. Now this is a composition of functions, so if we want h prime at 2, we would need to figure out what h prime of x is, and this is equal to the derivative of the outer function evaluated at the inner function, and via the chain rule we need to take the derivative of the inner function as well. And so if we want to put 2 in for x, what do we have here? So h prime of 2 is going to equal to f prime of g of 2. Let's take this to be the first value that we find. This is just a regular g evaluated at 2, and that's 5, times g prime of 2, and so we'll find this one, g prime at 2 is square root of 2. We're not quite done yet. We need to actually find out what f prime of 5 is equal to. So let's figure out what that is. F prime of 5, this is f prime at 5. It looks like it's going to be pi. So this is equal to pi, and you had the square root of 2 there, so that would be your solution. Next, this is I think this is supposed to be a product, so we have a product rule, a quotient, and some square root business happening there. So let's see if we can figure this out abstractly. What is our h prime of x? So this looks like it's going to be a little long. The first one is going to be the derivative of the first times the second plus the first times the derivative of the second. So that's the product rule business. After that, it's a quotient rule. So it's low d high. Now the d high is something, it's a f to the 1/2 power. So 1/2 times f of x raised to the negative 1/2 power times the derivative of f of x. So this is a long derivative for taking the derivative of the numerator, but this is the derivative of the whole numerator right here. So it's low d high minus high, and then d low is just the derivative of g, which is g prime, all over low squared. Okay, now let's put 2 in for wherever we see an x. So f prime of 2, g prime of 2, f of 2, g prime of 2, minus g of 2 times 1/2 f of 2 to the negative 1/2 power times f prime of 2 minus the square root of f of 2, g prime of 2, all over g of 2 quantity squared. Didn't know if we needed to have written all those again, but we did it anyways. Let's find the values. So f of 2 is e. I'm sorry, f prime of 2 is e. G of 2, that's just the g of 2, that's 5. F of 2 is also 5. G prime of 2 is square root of 2. So that's the first part. G of 2 is 5 times 1/2 f of 2 is 5 to the negative 1/2 power, and f prime of 2 is e. We have the square root of f of 2, which is 5. G prime of 2 is square root of 2 all over g prime, or g of 2 squared. Okay, I would probably just leave it at that, not bother simplifying or anything, but that would be your result. A couple more theory type questions. Proving a formula. When you have a function, there should be a few things that you should know, and I think for this formula I probably should have stated that you can use this particular formula, that the derivative of any number constant raised to a power is equal to that very same thing times the ln of that constant. Okay, we've actually used this a couple times earlier in the exam, and so this is the formula that we're going to prove. So the way we're going to prove this is we're going to assume that this is y, and then we know by the relationship of logs and exponents that if we take the derivative, or not the derivative, but if we just have this as a power of a and have this as a power of a, that your right hand side over here, a to the log base a of x, is equal to just x. That's just an identity. So let's rewrite that. A to the y is equal to x. So now at this point we're going to ddx this, and the formula that we're going to use comes in right now when we take the derivative of a to the y. Derivative a to the y is a to the y ln a times the derivative of the inside, in this case it's y prime. And the derivative of x is equal to 1. And so y is equal to this whole thing, so we're going to solve for y, or I'm sorry, yeah, y prime. Y prime is what we're solving for. Y prime is equal to 1 divided by a to the y times ln a, if we divide through by this thing. Now what is a to the y? Remember that our y is equal to ln x, a function of x, so that means we want our y prime to be just x's. And what is a to the y? Well, we can find it from here, but we also can find it from here. A to the y is equal to x. So y prime is equal to 1 over a to the y, which is x, times ln of a. And so that is the formula. And we've proved it using the chain rule and using what we know about the exponential derivative. Okay, this last theoretical question is asking us to find 2013 derivatives. Wow. Definitely don't want to take the derivative 2013 times. Well, let's at least take the derivative 3, 4, maybe 5 times to see if we can find a pattern. So let's do y prime. So the derivative of cosine 3x is negative sine 3x times the derivative of the inside, which is 3. The second derivative The derivative of negative sine of something is negative cosine of something times the derivative of 3, but there was another 3 here before. So let's make sure that we are understanding that this 3 came from this 3 and this 3 came from this 3. So basically have 9, or 3 squared. The third derivative is equal to the derivative of cosine is negative sine, so negative negative become a positive sine of 3x times 3, and then you got two other 3's here, the 3 squared that you got from before. Again, let's identify where these things come from. The 3 squared came from those 3, and then the 3 that came out came from the chain rule. Let's take the fourth derivative. Remember, after the third derivative, the primes you get to lose count of the primes, so you start using the numbers in parentheses. The derivative of sine is a cosine of 3x times 3 from the chain rule. Oh, and then there's 3 more 3's over here, so that's 3 cubed. That came from here, and this came from there. Oh, look, also this is a cosine already, back to our original problem. And if we were to take one more, derivative of cosine is negative sine 3x times 3 times 3 to the fourth that came from up there. So we see that this is now similar to this. This is similar to this. And so because of those similarities, we see that this is probably going to come up with a pattern. But let's get this fixed up a little bit. This is negative 3 times sine 3x. That's the first derivative. The second derivative is negative again, and then there's two 3's, so we'll call it 3 squared cosine 3x. The third derivative is now positive, and there's two 3's in the third one, so that's 3 to the third. This is a sine 3x. And then the fourth one is positive 3 to the fourth, and now it's a cosine 3x. And we have the fifth derivative, 3 to the fifth. This is going to be a sine 3x, and this is negative. So without doing any more derivatives, you can probably imagine the next few derivatives. Without doing the derivative, let's guess, and this is going to be 3 to the 6th. This is going to be cosine 3x. And if we follow the pattern, the next one's going to be positive 3 to the 7th sine 3x. And then positive again, 3 to the 8th cosine 3x. Now, let's see if we can find the pattern. So for the first derivative, we have 3, second derivative 3 squared, so it looks like the powers are growing by factors of 3, or not the powers, but the constants are growing by factors of 3. So it looks like the 2013th derivative, y to the 2013th derivative, is equal to, I don't know if it's a plus or a minus yet, but we'll figure that out in a minute. We know that this is going to be 3 to the 2013. Now we have to figure out if it's a sine or a cosine. So we have a sine, cosine, sine, cosine, sine, cosine, sine, cosine. So it looks like it revolves by by it just alternates. So it looks like this is the first derivative, this is the second derivative, this is the third derivative, this is the fourth derivative, this is the fifth derivative. So it looks like the odd numbers will give you a sine, the even numbers will give you a cosine. So that's easy enough to figure out. This is 2013 is an odd number. Odd numbers give you sine. So this would be sine 3x. Now whether it's positive or negative is the next question. It's either something that relates with 1 or 3 and 5 or 6. So this is where the real key comes in. It turns out that we can look at this as cyclical in steps of 4. So your original function, your y is positive sine, or I'm sorry, your original function, let me do it this way. Your original function is positive cosine. Your first derivative, y prime, is negative sine. So this is, let's start this as 0 starting point. This is 1. Your derivative of sine is your second derivative here, is negative cosine. We'll call that 2. After the cosine, we have positive sine. Your fourth derivative, your third derivative, sorry, third derivative is positive sine. I'll call that third derivative. And then your fourth derivative is cosine again. Your fifth derivative is negative sine. Your sixth derivative is negative cosine. Your seventh derivative is positive sine. And your eighth derivative is positive cosine. So if you follow this along, all the positive cosines would fall under 0, 4, 8, and if you can guess the next couple of derivatives that would give you a positive cosine, it's 12 and 16. It looks like it's by 4s. Now this one, you can think about this in a couple of ways. You can think about it this as adding 4s. So 1 plus 4 is 5, plus 4 is 9, plus 4 is 13, plus 4 is 17. Over here, 2 plus 4 is 6, plus 4 is 10, plus 4 is 14, plus 4 is 18. Over here you got 3 plus 4 is 7, plus 4 is 11, plus 4 is 15. And then you can see how this follows along. We got 3, 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10, 10 to 11, 11 to 12, 12 to 13, 13 to 14, 14 to 15, 16, 17, 18, etc. So again, it's still too hard to count by force to 2013. So the other way to do this more mathematically is that if you notice that the remainder, if you were to take any of these numbers, 5, 9, 13, or 17, and you divide it by 4, the remainder is going to be 1. If you do the same thing with 10 or 14 or 18, you divide it by 4, the remainder is going to be 2. Or if you took 7 and 11 and 15, you divide by 4, the remainder is going to be 3. So these numbers here turned out to just be remainders. So if you take 2013 and divide it by 4, and the remainder here is going to be either 0, 1, 2, or 3, because it's divided by 4, and then that remainder is going to match with the first, second, third, or fourth derivative. So let's do the division. This is 5, that's 20, and this is 1, so that's 0, and 13. 13 goes into 4 goes into 13, let's say 3 times, and then you get a remainder of 1. So we saw 13 over here, that's a remainder of 1, so that's a remainder of 1. So we have a negative sign, we got the sign correct, and now we have the sign, SIGN, correct. So this is the 2013th derivative of our function.